So this is the simple data set I'll be using. It's the same data I used in the R video showing how to estimate time series regression. It's just a simple data set for a production function rather, with Q, output Q, depending on capital and labor, K and L. Now, the first thing we need to do is to put the data into natural logs, because normally we're going to estimate production functions using natural logs. So to do that, of course, all I need to do is to use the built-in ln function. So I'm going to use a small letter here for the log. So let me put some headings. Like that. I'll just make them bold and center them. Okay, so now I can use the ln function. Like that. Copy across to do the rest. And then copy down to do all the other ones. So here's my data 9 natural logs. Now I'm going to show how to estimate time series data here. I'm going to run estimate a first order error correction model, the same one as I did it again in the R video. And this example, of course, is taken from a book by Thomas called Introductory Econometrics. Now, a first order error correction model involves running a regression where the change in the the first difference in the dependent variable, in this case Q, so the first difference of Q is regressed against the first difference of K, first difference of L, and the first lags of Q, K, and L. So I need to create those lags and difference variables. And of course, this is typical with time series data, that you'll be using lags and differences, first differences, perhaps even second differences, and so on. Now, obviously, again, in a package like I, you can use commands to do this. Here in Excel, we can do this very easily. The first thing I want to do is to lag each variable. Now, the notation I use for this is underscore and then a 1 if it's the first lag. So I'm going to put Q underscore 1 here, and then K. That's fairly obvious notation, which reminds me it's the first lag. Now, what the lag means is of course, is that we're going to use the previous period's value, in this case the previous year's, it's annual data, alongside the current value. So what this effectively means here in Excel is that you need to drop the variable, the data here, down one row. So that in 1961, for example, we'll regress the current value against the previous value of 1960. So I'm going to highlight all these, copy them. Now, these, remember, were created using a formula, so I can't just paste the formula here, otherwise it will reevaluate the formula and it'll all be wrong. I just need the values. So I'm going to drop down one row to here. I'm going to right-click, and then I can choose Paste Special Values, where in fact there is an option here already, as you can see, Values, which you can use more quickly. If not, simply go into Paste Special and choose Values, and that will do it. So notice I want to click the values here. If I just paste what's in those cells, I'll be pasting the formula, which will get recalculated, and you won't get the right answer. So there we are. I've dropped those down. Now, of course, creating lags and so on loses observation period. So as you can see now, when we run a regression here, 1960s values will no longer be included. Of course, these values at the front here, of course, are outside the sample period, so these are no good either. So I'm going to clear those just to tidy things up. Okay, so now I've created my lag variables. I can create the first difference of each variable, and that, of course, is simply the current value minus the previous value. So using, again, some fairly obvious notation here, a capital D for first difference. So this is dq, dk, and dl, so the first difference. Again, I can quickly create these by simply finding the difference between the current and the previous value. So for dq, it's obviously going to be this one here, which is the current value, 961, minus the previous value. So as you can see, having dropped them down a row, that makes that very easy. Now, if I copy across, that should do the other ones, like that. As you can see, that will be G3 minus K3, yeah. And this one will be H3 minus L3, yeah, so that's fine. So now I can copy down to do all the rest. And there we are. So it's very quick. It doesn't actually take very long to create these lags and these difference variables in Excel, particularly if you take advantage of the ability to copy formula like that. So that's fairly quickly done. So now I'm going to run this ECM model, this first order error correction model. dq will be my dependent variable, and my independent variables will be dk, dl, and these lags. Now remember, of course, that all the independent variables have to be adjacent to each other. So what I need to do is to move dq over here so that the other ones are together. So I'll do that. Just remember, you can right-click, go to the border, choose the right, hold down the right mouse button and drag across here. Let go, shift right and move. And that does it very nicely, as you can see. Now that would be fine because all my independent variables here are next to each other. I prefer it, however, here if the difference variables come first, so that when I get the printout, those will be first. Well, I can easily reorder again. Just highlight both, right drag across, of course, to here, shift right and move, and there we are. So everything's nicely in order. So this is very quick once you get if you're in Excel. So now I can use the regression facility, of course, to run this regression. Okay, so into the data thing and data analysis. Now remember, I showed in the previous video that if you don't have this data analysis option, you'll need to load up the add-in by, of course, going to the insert menu and manage add-ins. But assuming you've already got that here, I'll bring up the data analysis 2-pack, and I want the regression package, of course. Okay, so now simply put in the dependent variable, which is dq. Now notice that, of course, I mustn't include d9060. That's been lost now because of the taking of the lag. So it's going to be here. The X range, now that they're all together, I can put those in the block. Remember, they have to be adjacent to each other, like that. I want a constant. This, as I say, is an ECM, an error correction model, order 1. I want the residuals, of course, to do the diagnostic tests. So everything's fine. And I will get my results there very quickly. And if I widen the columns, remember it scrunches them up. That will give me my results. Now, of course, you do need, of course, to replace what it says here with the actual variable names because it doesn't know what they are. So remember, from top to bottom is the same as left to right. So highlight these here. Let's copy them and then paste them, but of course transpose. So right-click, choose space, special, and transpose, or in fact, there's an option there to do it immediately. And there we go. So that gives me my results. So that was, as you can see, you can easily use lags and difference variables in Excel. You just need to create them, and it's quite easy to do. So let's look at now how to carry out some standard diagnostic tests on the residuals. And I'll first look at this graphically, as I did in the previous video. and then I'll look at a formal test. Here, of course, with time series data, it's autocorrelation, which is usually the main potential issue. Heteroskedasticity is not usually a problem. So as far as heteroskedasticity is concerned, I'll only look at the standard graphical procedure of looking at the residuals versus predicted graph. For the autocorrelation, I'll show how to run a formal test. Okay, so first thing we need to do therefore is to plot the residuals. Okay, so let me plot a line graph of the residuals. Like that. So let's put the title in. Okay, let's make it a bit bigger. Now, as you can see, this is fairly indicative of autocorrelation, probably of negative autocorrelation, because you can see the residuals oscillating from positive, negative, and so on. That's typical of negative autocorrelation. So we'll seek to confirm that with the formal test. Let's have a look at heteroskedasticity briefly by looking at the graph of the residuals versus predicted values, which we've used before. So highlight them both. Let's create a scatter graph now of those. Whoops, let me put the title in. There we are. I'll move it over here. Just make it a little bit bigger. Any indication of heteroskedasticity here? Possibly. That variance does seem to be widening a little here, although this value up here seems to be a bit of an outlier. Possibly these as well. So maybe that's what's causing the problem. But anyway, I'll not conduct the formal test here. I showed in the previous video how you could conduct a simple Lagrange multiplier formal test. So you can run that if you wish. Here I want to concentrate on the Lagrange multiplier test for autocorrelation, which is often known as the Broich-Godfrey test. Now, of course, there is also the Durbin-Watson statistic. That's actually quite tricky and tedious to calculate here in Excel. But in fact, it's not of particular use here because it cannot be used when you have lag-dependent variables. And indeed, it's the Broich-Godfrey test, the Lagrange multiplier test, has essentially superseded that as the standard test for autocorrelation. So that's the one I want to show, and that is relatively easy to implement as you'll see now. So what this test does is it runs a regression of the residuals here against as the dependent variable against the original independent variables from our equation, plus various lags of the residuals. One lag if you want to test first order autocorrelation, 2 lags if you want to test second order, and so on. And then the test statistic, which is again a chi-squared statistic, so it's a large sample test. So in fact here we probably haven't got insufficient observations to give us a real good test here, but for illustration purposes this is fine. The test statistic, as with the heteroskedasticity test I looked at in the previous video, is given by nr squared, this number of observations times the r squared value. And then you can look at the p-value of that to see whether the test is the null hypothesis of no autocorrelation. The null hypothesis here is no autocorrelation, to see if that's accepted or rejected. Okay, so what I need to do therefore is to copy these residuals over to my data set and create some lag. So what I'm going to do is create a column here for the residuals, because remember I want to keep all the independent ones together. So I'm going to right click here and choose insert to give me a column here where I can put in the residuals. I'll just call them res rather than residuals. So that will give me my dependent variable. Then my independent variables will be these, the original ones, plus various lags of the residuals. So let me, using my standard notation, create the first column for the first lag, and for the second lag, so I'll test both first and second order autocorrelation here. So all I need to do now is to copy over these residuals here. I can then lag them once, like that, and then again, like that. So as we've seen, that's how you lag variables. You simply drop them down an appropriate number of rows. These ones now drop out, so let me clear those. Now notice that is losing observation periods. However, in this particular case, but only here, not in the case here where we lagged the actual dependent variables, but here where you're carrying out this autocorrelation test, it's permissible to put zeros in to keep to fill in those missing values, so that the sample size, number of observations, stays the same as in the original regression equation. Okay, but notice it's only in this particular case. Okay, so now I can run a regression of residuals against these original dependent variables plus the residuals lagged ones, first of all, to run a first order test. So let me go back to my regression facility. Let's delete what we had in before, because it remembers that. Sometimes that's useful, sometimes not. Okay, so the dependent variable y range is residuals there. The x range is the same independent variables plus residuals lagged once. Okay, so making sure you've got the same number of observations for both ranges. If not, you'll get an error and it won't work. So this is going to be this is an auto test, a test of first order autocorrelation on that EC1 equation that I ran. So actually I put an appropriate tab title there to tell me that's a test of first order correlation on this ECM1. Don't need the residuals of this, of course. So let's run that. And we get our results here. Again, widen the columns. Okay. I'm not going to bother copying over the variable names because I don't particularly want to look at those. You could, of course, look here at the coefficient of the t-stat on that residuals variable. Notice it is significantly different from 0, which is indicating first order autocorrelation, but the proper test is the chi-squared test. So let me create the chi-squared test statistic, which has 1 degree of freedom here because we're testing first order autocorrelation. And as I say, it's again equal to n, number of observations, times the r squared value. So that's that. Let's find the p-value as I did before in the previous video. Remember, you use the chi-squared.dist.rt function, which requires the test statistic, comma, and then the degrees of freedom, which in this case is 1. And as you can see, that is definitely less than 0.05. So the null hypothesis of no autocorrelation is clearly being rejected here. Let's quickly run the second order, although we've already got it in first order, but let's see if it's second order as well. So again, it's easy enough to do. I can simply include the second lag now of residuals. So notice my dependent variable is still fine, of course. I just need to extend the independent variables here to include the second lag as well. Again, just check the same number of observations. Yep. This is a test of second order. As you can see, it's very quick to do once you've got it set up. There's the results. Test statistic. 2 degrees of freedom. N times R squared. Again, that's very high, so that's almost certainly going to be significant, different from 0. Two degrees of freedom this time. And again, well below 5%. In fact, it's below 1% as well. So there's clear evidence here, as we saw from the residual graph here, clear evidence of autocorrelation here. So that, of course, would need to be dealt with in some way by either calculating robust standard errors, but of course which is very difficult to do here in Excel, I'm afraid. You can get that, of course, in a statistical or econometrics package, or to estimate the equation allowing for the autocorrelation, perhaps with the Cochrane-Orcutt method, or in fact, what autocorrelation suggests is that as the lag structure of the equation is wrong. So in fact, running an ECM1 here would appear not to be correct. We perhaps need to use a second order autocorrelation, second order error correction model, I should say, here. And in fact, if you look in Thomas's book, from which I've taken this example, you'll see that he shows that is a preferred equation, preferred regression. Okay, so that hopefully shows you how you can do regression analysis, also some basic regression analysis with time series data in Excel.